Alrighty, good morning everybody. Welcome back to Calc 1. Plan for today is we're going to jump into Standard 16 and start talking about graphical properties of the second derivative, including the second derivative tests. I've got my usual office hours today and Wednesday at 11 and 2, tomorrow at 11 and 1. And as far as homework goes, I just, before class, I posted a new web work assignment, homework 19, to be due on Friday. And on Wednesday, we're going to have a quiz over Standard 15. Dr. Verstel, you said we were going to talk more about Standard 15 today. I changed my mind. We're running a little bit behind where I'd like to be at in order to get through kind of a couple really exciting results towards the end of the semester and the last couple of standards. So I'm just not going to ask you any challenging or particularly nasty extreme value theorem problems is what I have to say. Exams. I just passed back the exam. Laura and Elise, if you want to come grab your exams from the front of the room, you can. Not everybody's taken the exam yet. I've got a couple of students who are going to take it over the next couple of days. Once everybody's taken it, I will post solutions on campus. But in the meantime, if you would like to come by and ask me about something, you're certainly welcome to. And yeah, just so you know, last midterm, there's one more midterm. Will be the final day of the semester. And then there will be a final exam. Both of these will have questions on every single standard. So, including standard 1, standard 2, etc. And I'm going to make you all a deal. If there's any standard that everyone in the class has 2 masteries in by the time of the third midterm or the final exam, I'll give you a joke in place of a question on that standard on the exam. That's a big if. Everybody has 2 masteries, otherwise I have to get the question also. Speaking of which, what did the mathematical acorn say on the day it grew up into a mighty oak tree? It said, "Gee, I'm a tree." Geometry. Geometry. Okay, so here comes the Standard 16 packet. This is one of the shortest packets I've ever passed out. And hopefully, I'm hoping to get through this one within a class or a class and a half. One, two. Okay, this time I remembered to put the front page graph actually up in your packet, so you don't have to draw it yourself. So, if you recall, last standard, Standard 15, was looking at different types of extrema, local maxes and mins, absolute maxes and mins, and comparing that to how we can use properties of the first derivative to find where these points are for your function, namely local max, local min, use the first derivative test, find your critical points where your derivative is 0 or undefined, plug into a little number line and see where is f prime going from positive to negative or negative to positive. Turns out Standard 16 is going to be very similar, except instead of having a test related to the first derivative and how we can find a local max and local min using the first derivative test, we're going to have a similar sort of test that works using properties of the second derivative, f double prime of x instead. So, a couple definitions to start things up. We're going to say that in general, that a function f of x is going to be concave up over some interval if f double prime of x is positive, and it's going to be concave down whenever f double prime of x is negative. So, concave up, concave down. The way I like to think about each of these is if you have a concave up function, meaning your second derivative is positive, what does it mean? What does that tell you about the original function? Well, I would say if f double prime of x is positive, this means that f prime of x gets more and more positive as we go from the left to the right.
Wow. That's what we need sometimes.
It also means that math department chairs are butting into someone's business. Owing to the that's all my hands up. So f double prime of x is positive. What that really means is that the rate of change of f prime of x, the first derivative, is going to be positive. So f prime is going to be getting more and more positive as we go from left to right. Similarly to how if f prime is positive, meaning the function's increasing, our f of x values are getting larger as we go from left to right. So I would say what that means is our function is not necessarily going to be increasing over a concave up interval, but what it means is if we look at what's the derivative doing at various points as we go from left to right. Zach, what's happening to the slopes of these tangent lines the further to the right we get?
They're increasing.
Yeah, they're increasing. Specifically, the slopes are becoming less and less negative and more positive when you're looking at an interval over which f double prime of x is positive. And similarly, we can say that if our function is f double prime of x is negative, meaning our original function is concave down, that's going to tell us that f prime of x gets more and more negative as we go from left to right. So what would that look like graphically? For concave up, we have sort of this upright bowl where our slopes are becoming less negative and more positive as we move from left to right. Hey, Josh, what do you think the graph of a concave down function would look like?
It would just be flipped.
Does this just take this bowl shape and turn it upside down?
Yeah,
I like it.
the hill.
Yeah, it's going to be like a hill, meaning as we go from left to right, our slopes are going to be becoming less and less positive, and eventually more and more negative. Well, you can think, one way I like to think about it is if you have a concave up function, it's like an upright bowl. Upright meaning if I were to spill water into here, it would hold water. Whereas for a concave down function, it's like a bowl that's upside down. If I were to try and sprinkle water onto this, it would spill over the sides. The bowl wouldn't hold the water. So upright bowl for concave up, upside down bowl for concave down. Questions or comments so far? You all have 1 minute. I want you all to see if you can determine approximately where you think that this function, f of x, is concave up versus where is it going to be concave down. As always, talk to your neighbors. Feel free to ask any questions you might have. And we'll reconvene in a minute or so. See if we can determine where we think this function is concave up versus concave down.
Do we have to do it in interval?
Yeah, well, we're going to write our answers in interval notation. If you feel like you have an answer, like you have an answer to, oh, I think it's concave up here, concave down there, turn to your neighbor and see if they agree with you.
Yeah, the answer.
One's right here. Oh, okay. Wait a minute.
Said 0, but I think
I didn't know about like the left hand, right, whether it be negative infinity or.
what do you say the limit is?
I'm just saying it's here, from one,
Is that what you had?
not actually close to one, increasing slope.
Yeah, you're how many years
So that's why I'm including one.
I mean, quarter.
The concave down,
More.
negative 2.
I don't do dishes. It was at Chloe's house, it wasn't at Tom's. I always do that, just like glasses, Does she have a lot?
I don't know.
It's not like really her.
I could be wrong, I don't know.
Stuff. Oh.
Alrighty, sounds like conversations are starting to die down a little bit. So let's see what the class consensus is. Would anybody like to propose an interval where they think this function is going to be concave up? Alright, from -2 to 3? Well, what do you all think? Does it look like for all values of x from -2 to 3 that our slopes are going to be becoming more and more positive as we move from left to right? Rachel?
I think it's closer to like -1 to 2-ish.
-1 to
Or
2?
maybe -1 to 2.
It's a little bit harder to tell. It's a little bit hard. Also, this point's supposed to be over here. I should probably try and make the graph on the board somewhat match up with what's going on the page. Why do you say only from -1? Starting at -1 instead of -2?
Because at -2, the tangent lines are still like starting to get more negative.
Yeah, so if we were to graph out like a tangent line at -2 versus like -2.1, it looks like our slopes are becoming more and more negative still. Right?
Could you just not put the one and then like could you just say -2 is less than x is less than 3?
Like that? Well, let's see. If we look at just a little bit to the right of -2, still looks like our slopes are getting a bit more negative for a little bit to the right of -2. So I think I actually agree with you, Rachel. I think it's probably going to start at something a little bit closer to -1. Because at -1, and our slope's pretty negative, starting at that point, our slopes is starting to become a little bit more and more positive as we move to the right. It's at -1 that we're really starting to transition, in other words, I would say from this upside down bowl shape to the right side up bowl shape. And then, let's see. And so then Rachel, you said that it looks like you think it looks at about x equals 2, that it stops being concave up and starts being concave down?
Yes.
Let's take a look. Here, I would say up until 2, it's looking pretty positive with our tangent line slopes getting more and more positive. And then once we get past 2, it's a little bit hard to say. 2.5. Something like that. Riley?
Is it the point where the slope of the graph is like a vertical line? Is that where the integral suddenly starts?
Not necessarily. Like here, for instance, I don't think that the slope ever becomes entirely vertical. It gets pretty close to it, but it's still just, I would say, a steep positive slope rather than a completely vertical one. Like this, like f of x, at least I tried to draw it in a way that makes it so it's differentiable everywhere. There's no vertical tangent lines going on. But I would say that it's going to switch at the point where our slopes stop becoming positive, more and more positive, and start becoming more and more negative. So if our function is going to be concave up for everywhere between -1 and 2.5, where's our function going to be concave down? Yeah?
Negative infinity to -1.
Okay, so from -infinity to -1, okay, well, let's try and make this at least look like it's a function. I would say that, yeah, looks like our slopes are becoming more and more negative. That's no matter how far out to the left we go, and then at -1 it stops becoming more and more negative, it starts becoming more and more positive. Anywhere else, Hannah?
Yeah, and then from 2.5 to infinity.
Over that interval?
Yeah.
Yeah, and then once we get past x equals 2.5-ish, our stopes start becoming more and more negative, or less and less positive, and more negative as we go to the right. And of course, if you want, you could also write this using this form of interval notation as well. That's just a personal preference. So what's the moral of the story here? Would you say looking at a graph like this, is it easier or harder to determine where a function is concave up or down versus increasing or decreasing? So in other words, if you look at a graph of a function, is it easier to tell looking at a graph where f prime is positive or negative, or where f double prime is positive or negative? Let's put it to a vote. Thumbs up if you think f prime, it's harder to tell looking at a graph where f prime is positive or negative. Thumbs down if you think it's harder to tell from looking at the graph if f double prime is where that's positive or negative. 1, 2, 3, vote. Few sideways thumbs. Avery's being a little bit contrarian and vote thumbs up. I think I see more thumbs down. I think I would agree with the class consensus here, in that in general, it can be pretty tough to determine where exactly a function is concave up or concave down. It's like we kind of struggled, like, it looks like somewhere between 2 and 3. Honestly, I would say probably closer to like 2.2 or something. Where the function stops being concave down, or stops being concave up and starts being concave down. And then it looks like -1-ish it's swapping from concave down to concave up behavior as we go from left to right. But in general, I would say, as moral of the story, if you were to ask me where does this function have a positive first derivative, meaning where's the function increasing, I think that's a little bit easier to say, oh, it's increasing from negative infinity to negative 2, increasing from 1 to 3, and decreasing everywhere else. It's a little bit easier to just kind of see that. You don't have to eyeball it and say, it looks like it's approximately here, I would say, as much. So I would say, as a moral here, we could say it's easier to tell graphically where, let's say, f prime of x is positive than where f double prime is positive. Any questions or comments? So if we look at our graph for kind of something that looks concave up and something that looks concave down, what appears to be happening at these 2 points? Let's start with the concave up function. What's happening at this point right here at the bottom of the bowl, so to speak? What type of point can we say that our function has there? Art?
A minimum.
Yeah, this is going to be the location of a local minimum, potentially an absolute minimum if it keeps going up as we go to the left and right as well. And let's see, when I think you had your hand up. How about for our concave down function? Yeah, I would say this is going to be the location of a local and potentially an absolute maximum to our function. And it's pretty much going to turn out to be the case like that. This is always going to be true, that if you have sort of a critical point of a function where it's concave up, you're going to have a local minimum. If you have a critical point like this, where your function is concave down, you're going to have a local maximum. And if we flip to the second page, we're going to have the theorem called the second derivative test this time that's going to tell us that. So here's where we said concave up. Here's where we said So second derivative test says that, similarly to the first, that if f of x is continuous everywhere, then we can say that f of x is going to have a local maximum at x equals a if f prime of a is equal to 0 and f double prime of a is negative. And similarly, we could say that f of x is going to have a local minimum at a point x equals a if f prime of a is 0 and f double prime of a turns out to be some positive number. So for instance, if we look at this interval on the left, where we said that our function is concave down, meaning f double prime is a negative number, at what value of x does it look like we're going to have a local max or a local min over kind of that left-hand side of the graph? So in other words, at what value of x, sort of looking at this, this concave down portion of the graph here, does it look like we're going to have a local max or min, Helen?
Around x equals 1. -1. -2.
There's a that tick mark sort of got lost in the shuffle there. But yeah, I would say at about x equals -2, we have something going on. And what type of did he say? Is it a max or min?
It would be a local max.
Yeah, I would say that at here, this point here, we have a local max at this point where f prime is equal to 0, because the tangent line at that point is completely horizontal. But the second derivative, f double prime, is going to be negative, since our function's concave down. It has this upside down bowl shape at that point. And so what the second derivative test tells us is that anytime that combination happens, where f prime is 0 and f double prime is negative, we're always going to have a local max like that. And I think we could say similarly that at about at x equals 3, the same thing's going to happen, where f double prime is negative and f prime equals 0. So we're going to get a local max at x equals 3. How about in the middle of our graph, over the interval where our function is concave up? There any, does it look like there's any local extrema in there? Josh?
A local min at x equals 1.
Yeah, it looks like we have a local min at x equals 1. And if you notice, at x equals 1, we have that f prime is 0, because it has a horizontal tangent line there. And f double prime is going to be positive, since we have this up, right side up bowl shape there. Bowl shape that'll hold water. And so second derivative test is just kind of generalizing these observations that you made. That anywhere where your first derivative is 0, and if your second derivative is positive, meaning if you have a concave, if your function is concave up at a critical point, you're going to have a local min. And if your function is concave down at a critical point, you're going to have a local max. So Dr. Gerstel, what happens if f prime is 0 and f double prime is also 0? Josh, Zach, I like how you made like pretty much exactly the same like facial gestures right there, like a split second apart. Like, any observations?
We don't know.
We don't know. Other than the fact that that's what it says in the packet. Let's see what it said. Let's look at a couple examples and see what if f prime equals 0 and f double prime is equal to 0. So I'm going to give you a function where f prime and f double prime are both going to be 0 at the exact same point. And the function is going to be f of x equals x cubed. Which if we look graphically, looks something a little bit like this. Mackenzie, we look at this graph, at what value of x are both our first and second derivatives going to turn out to be 0? Yeah, I would say at x equals 0. And we could check. If we tried to take f prime of 0, that would be, what, 3 times 0 squared, which is 0. And if we were to do f double prime of 0, we would get 6 times 0, which is still 0. So f of 0 and f double prime of 0 are both 0. So what type of extremum do we have at 0? Do we have a local max or a local min there? Well, neither. Gadzooks. Yeah, I would say that at x equals 0, in this graph, f prime equals, f double prime equals 0, but no max or min. So we could potentially have neither a local max nor a local min at a point like 0 like this, where our first and second derivatives come out to 0.
If f double prime equals 0, doesn't that mean that like it's always either going to be a local max or min?
Good question. Let's look at another example. Let's look at g of x equals x to the 4th. Which if we graph out, it's going to look something like this. So if we were to look at g prime of x, we would get 4x cubed. And g double prime of x is going to be 12x squared. We just applied the power rule a couple of times to this thing. Danielle, are there any values of x where both of these expressions are going to come out to 0? Yeah, we plug in 0 for x, 4x cubed, 4 times 0 cubed will be 0. 12 times 0 squared should just be 0. So we can say that this function at x equals 0, f prime and f double prime are both going to be equal to 0. Ryan, are we going to have a local min, a local max, or neither at x equals 0 for this function? Looks like a local min. Turns out it is a local min. So then to answer your question from a minute ago, I would say that no. If we know that f double prime is 0, it could mean we have neither a max nor a min, like in the case of x cubed here. But we also could be in the case of a function like x to the 4th, where even though our second derivative comes out to 0, we still could potentially have a local min or a local max. And so that's why that it does in fact say in the packet that if f prime and f double prime are both 0, it's unknown whether we have a local max or a min at that point. Because sometimes you could have a function where f prime and f double prime are both 0, and we have a local min, or potentially a local max. If you want a local max example, just take negative x to the 4th and flip this graph upside down. But we also could have something like x cubed where we have neither a max nor a min at our point where f prime and f double prime are both 0. The second derivative test just doesn't tell you anything in that scenario if f prime and f double prime are both 0, and so life gets a little bit sad if that's what ends up happening when you look at your function. Yeah, it does.
So basically, as long as x is to some even power, there'll always be something.
If all that you have is a function of the form x to the n, then yes. Typically, and the reason is if you have something like f of x equals x to the n, where n is odd, you're going to have a graph that generally does something like that. And if you take a function like f of x equals x to the n, where n is even, it's going to have usually this general shape to it that sort of looks like an upright parabola. Yeah, good observation. The tricky part comes, what if we have different powers showing up? Like, what if I gave you f of x equals x to the fourth minus 3x cubed plus 2x squared minus x plus 5? Then it's not so clear cut. I just made up that example on the spot, and I have no clue what types of critical points that thing has. So you would have to go do a little bit of testing for that. So moral of the story, though, is that in order to use the second derivative test, you need that your first derivative is 0, so you have a critical point there, and your second derivative has to either be positive or negative at that point. If both are 0, you're out of luck. If f prime does not exist, you're also out of luck. So we can say that the test is going to end up being, I would say, unhelpful in either of those cases. Unhelpful if either f prime of a does not exist, or f prime of a equals f double prime of a equals 0. Because if you recall back to the first derivative test packet, standard 15, we said if you have a local max or a min, then it has to be at a critical point, meaning a point where f prime is either 0 or undefined. But if it turns out to be at the undefined type of point, then second derivative test doesn't tell you anything. It just ends up being unhelpful. And so I would say if you're in that sort of situation where you find, oh, f prime does not exist, or the second derivative is also 0, use something else. Use the first derivative test instead of the second. Any questions or comments so far? Let's do an example. So we flip the page. I want to find all local extrema, local maxes and mins. For the function f of x equals 2/3 x cubed minus 7x squared minus 16x plus 10. And just like the progression we made in standard 15, this time I'm not going to give you a graph of the function. And it's going to be up to you to determine where does this function have local max and or local min. So what do you think would be a good first step? Laura?
Take the first derivative.
Take the first derivative. Groovy. What do you want to do with it once we have it?
Take the second derivative.
Groovy. Once we have two different derivatives, what do you want to do with them?
And then set the second derivative equals 0. And find out where it is equal to 0.
Okay. Actually, I think we are going to need to find f prime and f double prime. But if we want to find our potential locations of local maxes and mins, I actually think we need to start by doing the same thing we did for the first derivative test. We need to find our critical points where f prime, the first derivative, is 0 or undefined. So let's start by doing the same thing. Find our critical points. So So Laura, what is f prime of x going to be in this case?
2x squared minus 14x minus 16.
So we have our f prime of x, 2x squared minus 14x minus 16. We don't have to worry about this ever being undefined since it's a polynomial. So I think we can just set this equal to 0 to find where our function has a critical point. So how do we solve this equation? 2x squared minus 14x minus 16 equals 0. Kinsey? Factor out of what?
Factor it to find x.
Ah, okay. Factor to solve for x. Cool. So what can we factor here?
I would factor out a 2 first.
Okay. So we get x squared minus 7x minus 8. We did that.
And then it would be, you would divide both sides by 2, so then you would be able to factor the function. And it would be x minus 8 times x plus 1.
X minus 8 times x plus 1. So let's see. X squared minus 8x plus x would give us a minus 7x. And then minus 8 times a plus 1 will give us a minus 8. I'll like it.
So then our 2x plus our x equals 8.
X equals 8 and x equals negative 1. Everyone on board with that? Dr. Gersel, could we have used the quadratic formula? Yes, you can use the quadratic formula. So these are our two critical points, which means these are going to be points where f of x could have a local max or min. I say could because we don't necessarily know yet if we do happen to have a max or a min. And what I want you to notice is so far, everything that we've done is exactly the same as if we were going to use the first derivative test. Because if you want to use the first derivative test to find local maxes, local mins, you use the same procedure of starting by finding your critical points. But now, I think, is where we're going to diverge from the first derivative test. So second derivative test tells us that if f prime is 0 and f double prime is positive, we have a local min. If f prime is 0 and f double prime is negative, we have a local max. So what do you think we can do next that would help us, that would allow us to use the second derivative, f double prime of x, in order to determine if we have a local max or a local min, or potentially neither at x equals 8 and negative 1. Josh?
Find the intervals and where it's like increasing or decreasing so we can get like a general idea of a graph and
For f prime of x?
yeah.
So it sounds like you want to use the first derivative test?
Oh wait. Can we just integrate it again and then get the second derivative?
Integrate it?
Oh my lord. Take the derivative.
It's a Monday. I'm all over the place too. All right, I like Josh's idea of differentiating a second time for to integrate and get back to what we started. So now let's look at f double prime of x. So Josh, what is f double prime of x going to be?
Would be 4x minus 14.
And the minus 16 goes away?
Yeah.
I like it. Vanishes into the ether. Okay, so we know where our second derivative is. It's 4x minus 14. Now that we have our second derivative, what should we do with it?
Plug your critical point values in for x and see if it's positive or negative.
Okay, if we plug in, let's see, we'll start with 8. That'll give us 4 times 8 minus 14, which is 32 minus 14, which is 18, which is some positive number. And if we plugged in -1, we get 4 times -1 minus 14, which is going to be -18, which is negative. All right, Wynn, I did what you asked. What does this tell us?
So if it's negative, that means there's a local maximum. If it's positive, it means there's a local minimum.
Yeah. If you recall, second derivative test says if f prime is 0 and f double prime is positive, we have a local minimum. Where am I pointing? At our point. And I think that's what's happening here, is we can say since f prime of 8 was 0 and f double prime of 8 is positive, f of x is going to have a local minimum, at x equals 8. And similarly, let's see, John, what can we say is happening at x equals -1?
There's a local max.
Because f prime is 0, but f double prime is negative?
Now I'm lost. What, can you ask the question again?
Sure. So here, since we said that since the first derivative was 0 and the second derivative was positive at x equals 8, the second derivative test told us that we had a local minimum at x equals 8. Here, we've also seen that f prime of -1 is 0. I am a competent human being who knows the difference between positive and negative and max and min. All right, now that I've reassured myself, f prime of -1 is 0, and f double prime of -1 turned out to be a negative number. What is that going to tell us f of x has to have at x equals -1?
A local max.
Yeah, like it is going to have a local max. Yeah, you were right the first time. I was just asking a clarification question.
Oh.
At x equals. So there we go. Once we found our critical points, which is the same as in the last packet, you just take the derivative, see where it's 0 or undefined. We just have to plug our critical points into the second derivative to see if we get something positive or negative. And if f prime is 0, but f double prime is positive, we have a local minimum. And if f prime is 0, but f double prime is negative, we have a local maximum. Just like what happened with our function on the front page. No fuss, no muss, no coconuts. No having to mess around with drawing out a number line and checking what's the sign of f prime on each side of our critical points. If we had done like the first derivative test technique, which Josh, I think you had suggested originally, what we would have found is we would have gotten something like this, where f prime is 0 at those 2 points. It's going to be positive to the left of -1, negative to the right of -1, positive again to the right of 8. And we would have gotten the same answer in the end. We would have just had to check f prime of a few other points along the way. We would have taken like f prime of, I don't know, -2, f prime of 0, f prime of 9, plugged all those numbers into this equation, and then seen, or not the equal 0 part, but into this function and see whether they came out something positive or negative. And the first derivative test, though, would have gotten us to the exact same point. Any questions or comments on this one? Okay, so next up, how did we do? Doing good on time? I want you all to take a look at a function and try one out for yourself. I'm actually going to flip to the back page here. There's a second one on the third page that you're welcome to try. I want you all to take a couple minutes and see what happens if we apply the same process, except this time our function is going to be g of x equals x to the fifth minus 5x to the fourth. So go ahead and take a couple minutes and see if you can use the second derivative test to determine where does this function have a local maximum, where does this function have a local minimum. As always, you're welcome to talk to your neighbors and or to ask me any questions you might have. I put a hint on the board too. Okay, there it is. So what can you do that would make you a little more sure about it? Is there any other technique for determining what's going on? I'll give you a hint, there's two critical points as well. So if you only found one critical point, you might want to take a second look. Oh, I forgot to ask, what happened to your package? Packed up and ready to go. once you feel like you have something, turn to your neighbor and see if they agree with you.
You just put we don't know for.
Yeah, it's either.
Okay.
Or when we don't know, it's unknown. It could be anything.
Is that the electrode?
We don't know what zero is.
We could find out by the first derivative.
Oh,
That's,
now there's a thought.
that's too much work.
That's too much work. That's nonsense. Too much work. Call yourself a Hillsdale student.
I guess so, man.
Okay, starting to sound like the conversation's dying down here. So, what are your thoughts on this one? Please? Gadzooks. How did you find the first? So, well, maybe let's start. How did you find your first critical points? Or your only critical point, I guess, if that's the case.
So I took the derivative and then set it equal to 0.
Okay. So, what was the first derivative?
5x 4 minus 20x cubed.
Okay. And you said you set that equal to 0. Groovy.
And then I factored out a 5 from the first one.
Okay, so I'll give us, what, x to the fourth minus 4x cubed?
And then I divided both sides by 5.
Cool. So that gets us to x to the fourth minus 4x cubed. Has to come out to 0.
That's where I kind of got stuck, because the only thing I could think of to do is factor out x cubed, but that only gave me
Okay, so I like this idea. So you factored out an x cubed. So if we do that, what are we left with inside?
x minus 4.
Like that?
I think that I could divide both sides by x cubed, but that only gives us one critical point after that.
Okay, so what critical point would that have given us? So this tells us we have a critical point at x equals 4. Would it help, at least if I rewrote this slightly? If I rewrote the x cubed as x minus 0 quantity cubed. Or where would our other critical point be at? What?
You could set x cubed or x minus 0 cubed 0 as well, and get your other critical point at 0.
Yeah, I think we're going to get a second critical point at x equals 0. Because at least I like your work here, where you factored out an x cubed and said x cubed times x minus 4 equals 0. Which certainly would allow, if x equals 4, that would make this term equal to 0, and so the whole thing would come out to 0. If x were equal to 0, you could also make the x cubed term come out to 0, which would still make the whole thing turn out to be 0. So we got 2 critical points, one at x equals 0 and one at x equals 4. Neato burrito. What should we do with these? When?
Take the second derivative and then plug in your critical. You don't have to plug in 0, but plug in 4.
Certainly try plugging in both of them. All right, so if we do that, what's our second derivative going to be when?
20x cubed minus 60x squared.
Okay, so here's our second derivative, 20x cubed minus 60x squared. If we differentiate our first derivative, 5x to the fourth minus 20x cubed. So now, if we plug in our two critical points, we plug in 4, we'll get 20 times 4 cubed minus 60 times 4 squared, which my spidey sense is telling me is going to come out to 320, as per the hint. Which smells positive to me. Emily? Or, sorry, Mackenzie?
So it's concave up, so at x equals 4, f of x has a local minimum.
Yeah. So our second derivative is positive, so we have an upright bowl, and upright bowl plus derivative of 0 means local minimum at that point. So we can say since g prime of 4 equals 0, and g double prime of 4 came out to this positive number, g of x has a local minimum at x equals 4. I like it. And then, let's see, what happens if we plug in g double prime of 0? Josh?
You get 0.
We're going to get 20 times 0 cubed minus 60 times 0 squared, which is going to be 0 minus 0 equals 0. And so, Josh, what does the second derivative test tell us then has to happen in this case?
That it's unknown.
Gadzooks. Second derivative test doesn't seem to tell us anything here. Because if our first and second derivative are both 0, which is happening here at x equals 0, we could be in a case like with x cubed where we have neither a max nor a min. We could be in a case like x to the fourth where we have a local min, or potentially a local max. So I would say here, since g prime of 0 equals 0, and g double prime of 0 equals 0, the second derivative test tells us nothing. Leading to sadness. It told us what one of our critical points was. It told us our first critical point was a local min, but didn't tell us anything about our second critical point. Josh, have any ideas?
I was going to say, since it says using second derivative theorem, would you want us to kind of quiz to solve it? Anyway, even though it just says by
Nope,
SDT.
don't say to do that, man.
Luckily, our class work ethic does not stem from Zach. So it depends on what I get asked on the quiz. On the quiz, I would probably say something like, use the second derivative test, and if that fails, use another way to determine. So, is there any way that we could determine whether our function has a local max or min, or neither, at x equals 0?
Use the first derivative test.
Use the first derivative test. Let's try that. Question doesn't see. So here's a good rule of thumb. If the second derivative test fails, use the first derivative test. All right, our two critical points were at x equals 0 and 4. So if we plug those in on a number line, I probably should have written down what our g prime of x actually was. It was, 5x to the fourth minus 20x cubed? So we know g prime is going to be 0 at x equals 0 and x equals 4. Tyra, can you give me a value of x to the left of 0 where we can check the sign of g prime?
-1.
Okay, So if we do -1, we get g prime of -1 is 5 times -1 to the 4th minus 20 times -1 cubed, which is 5 plus 20, because -1 cubed is -1 times -20 is positive 20. We're going to get something positive to the left of x equals 0. And Vera, how about something between x equals 0 and x equals 4?
1.
Good choice. Prime of 1 is going to give us, I'm just going to say it's 5 minus 20 is -15. And then we could check to the left of 4, but I don't think we really need to. Or, sorry, to the right of 4. I know left and right. I'm a competent person. I don't think we need to, though, because we already know at x equals 4, we have a local minimum. Which means I already know this is going to have to be plus in order to get a local minimum there. So if we look at g prime here at 0, it looks like g prime is going from positive to negative. So it means we're going from increasing to decreasing with the original function. And so, Helen, what does that tell us is happening with g of x at x equals 0?
It goes from increasing to decreasing. Then you have local max.
Yeah, it's going to turn out that we have a local max. So we can say, then, since g of x, or since g prime goes from plus to minus at x equals 0, g of x has a local max. So before you all pack up and leave, I want to make a couple comments here. Which test did you prefer for finding local maxes and mins, first or second? Second?
For sure.
Even though the second derivative test ended up failing us in the second problem?
Yeah.
Well, you didn't go back and use the first test. Of course, you did. I would say that the moral of the story is, I personally think that the second derivative test is a little easier to use, and that you don't have to make the number line. You just have to take the second derivative and just plug in your critical points in, rather than checking points on either side. The problem is, the second derivative test can sometimes fail you, like it did with this one at x equals 0, whereas the first derivative test will never fail you. First derivative test never ends up with the sort of inconclusive thing that the second derivative test does. First derivative test will always tell you at your critical points if you have a max or a min. So first derivative test is maybe a little bit more reliable, but also a little bit harder to implement in comparison to the second derivative test. Second derivative test is easier, but sometimes conks out on you. All right, last thing.
Double quiz.
Do you want a double quiz on Wednesday or a single? Or would you prefer standard 15 Wednesday, standard 16 on Friday? Because we just finished standard 16.
Double.
Double, toil and trouble?
Yeah.
All right. Double quiz on Wednesday, and then we will do our Coke example where we pretend we're working for the Coca-Cola Corporation. Have a good day, everybody.